Good morning. We will continue our discussion related to the dispersion curves in phonons. We looked at the nature of the lattice vibrations, the corresponding relationship between the frequency and the wave vector, and also that in 3D crystals, so that you have the 3 modes, which are the longitudinal and 2 transverse modes, and also depending on the number of atoms in a basis, you can have either only the acoustic modes, or if you have a polyatomic chain, so then you are ending up with optical branches as well. So, the number of optical branches can be more than the acoustic branches. So, I have given you a thumb rule calculation for knowing how many optical branches are possible. So, all this is very good. Now, what we will do is, however, many times these actual dispersion curves are not used. So, as you can see, this nature of the acoustic dispersion curve is a sinusoidal variation. Okay. So, either people use at the most the sinusoidal variation in a simple fashion, or they use a even more simpler approximation, which is a linear approximation to this. Okay. So, you can also check the validity of this dispersion curves by doing experimental measurements. So, people have made experimental measurements, and then these are reasonably good approximations to the experiments. However, to even simplify this further, we can make an assumption. So, I will call this as the Debye approximation. So, the Debye approximation states that if you are looking especially at the lower values of frequency and wave vector, that is in this particular region, this curve is more or less approximated as a linear curve between omega and k. Okay. So, you can actually use this and extrapolate it to all the higher values of k, and the simplest way will follow a linear curve all the way from k equal to 0 to what? K equal to pi by a. So, this is called the Debye approximation. The corresponding value of omega, which will reach the maximum at k equal to pi by a, is called the Debye frequency. This is called the Debye frequency. And this is for the acoustic modes. So, in fact, you can make a similar approximation for all the acoustic modes, the longitudinal and the transverse. What about the optical modes? If you look at our representation of optical mode here, compared to the acoustic mode, the slopes are relatively less. Okay. So, the easiest approximation to this is called the Einstein approximation. So, therefore, we use the Debye approximation to make a linear approximation for the acoustic phonons, and the Einstein approximation for the optical phonons. So, and how would that be? If you are plotting, continuing this in the vertical line, so you will just end up approximating the optical phonons with just a horizontal line. So, this will be your dispersion for acoustic, and this is for your optical phonons. So, therefore, if you go back to our actual relationship between omega and k for a monoatomic crystal, we had derived this, right. So, let us call this as equation number 1. If you are making a linear approximation, okay. So, we can say that the linear approximation to this would be valid for small values of wave vector kappa, strictly speaking. Okay. So, in that case, in that range of small values of kappa, so what will happen to this expression? Can you please write it? So, therefore, for small values of, so now the Debye approximation. So, you have small values of kappa. So, in this case your omega will be square root of spring constant by mass times what? Kappa a by 2, 2 and 2 cancels. Okay. So, this is your linear relationship between omega and kappa. Okay. What I call k here is kappa. Okay. So, you please understand. So, what we will do is you have square root of k by m and a, these are constants for that particular crystal. So, you should know how you are approximating the spring mass system and what is the spring constant, what is the mass and what is the lattice spacing. So, therefore, if you look at the units of square root of k by m and a outside, can you check what is this unit? It will come out to be meters per second. So, this is basically your phonon velocity approximate. Okay. So, what we will do is to distinguish this from the actual phonon velocity which we obtain by taking the slope of the dispersion. So, we are going to call this velocity as the Debye velocity. Okay. Although this is also a velocity scale, this is not the exact phonon velocity that you obtain from this slope. So, therefore, we will correct it, we will call this as Debye velocity, okay, and therefore, your omega is equal to V Debye times kappa. So, this is your Debye approximation. Is that clear? So, this is a very simple approximation, but nevertheless when you want to investigate some problems where this is easier in the analytical solution. So, this is more commonly used than the sign approximation, and for more complex cases the sign approximation is used, and the optical phonons are now just approximated as omega is constant. Okay. Right. So, that means what do you infer from this about the velocity of the optical phonons? So, they do not travel at all. It appears from this approximation that the optical phonons are stagnant. Okay. So, they will be acting only like a capacitor, they will be taking the heat, they will be interacting with the higher electromagnetic modes of vibration. Okay. They will be taking the heat, storing it and releasing it to the acoustic phonons, but they will not however be travelling with a significant velocity. So, this is the approximation for called the Einstein approximation. So, now what we will do is next from these quantized modes of wave vector, we will go on and define quantity called density of states. We will do this for both electrons and phonons. Okay. So, what is this density of states? So, now if you wanted to plot, let us first do it on a 2-dimensional diagram, kx versus ky, a 2-dimensional crystal, okay, whose wave vector is quantized in both the x and y direction. You understand? So, just like you have a 2-dimensional quantum well, okay, so you can extend that to a crystal as well. So, you have quantized discrete states. So, therefore, if you want to have a lattice like this and divide this into equal segments, okay. So, you have equal segments here approximately, and if you look at our wave vector for the crystal, how does it vary? They are discrete 2 pi n by L, right. So, n can be plus or minus 1, plus or minus 2 and so on. So, therefore, what do you want this width of each mesh, each grid to be? Now, we can start the origin here. So, if we put n equal to 1, this will be 2 pi by L, plus or minus 2 pi by L, and then if you put n equal to 2, 4 pi by L and so on. Okay. So, therefore, the separation between these points will be 2 pi by L. Okay. So, the next will be 4 pi by L, then 6 pi by L and so on. So, therefore, what we are drawing is we are now plotting these discrete wave vector states on a map, 2-dimensional map, okay, and this map coordinates are labeled in spacing of 2 pi by L, because that is how the wave vector is actually quantized. So, therefore, this is one thing. Now, when you plot these states, relation between kx and ky, you will actually have some discrete representation of points in this space. Okay. So, what we are concerned is not each and every microstate here, but we will sweep some differential element of a circle or a sphere. Now, if you extend this to 3D, if you put plot also kz, you will end up having a spherical coordinate system, and when you want to cut off a small segment, a differential element, so that will be a differential element of a sphere. Okay. So, this differential element is indicated by basically your k vector, this first surface, and the outer surface by k plus dk, where dk is the width of this differential element in a wave vector space. Okay. So, therefore, now we are going to define the number of states between k and k plus dk. So, we want to now count the number of quantum states on this wave vector map between k and k plus dk, that is within this differential surface element, okay, spanned by the width dk. We want to count how many quantum states are accommodated in this map. Okay. So, we will also define this number of states per volume of the crystal. Okay. So, this is a number density kind of a thing. Okay. So, how do you calculate the number of states now? So, the area which is swept, so this is your cross sectional area here. So, the inner area, inner surface area will be 4 pi k square, right, multiplied by this differential control element width dk will give you this shaded area, correct. So, divided by your crystal volume. Okay. So, we will call this as V, okay, and therefore, no, just let us not jump 2 steps. So, just make sure you do not get confused. So, first we will calculate only the number of states. So, this will be basically this area divided by the volume of each unit cell here. This is your grid, right. So, what is the volume of this particular grid? So, this volume will be 2 pi by L whole cube, right. So, therefore, if I want to count the number of states between k and k plus dk, this is your actual area there divided by the volume of each unit block. Okay. So, this will give you the number of states between k and k plus dk. You understand? So, we have already represented this variation between kx and ky, and now we are culling out a small region, differential region. We are calculating that volume there. Okay. So, that volume is 4 pi k square dk divided by the volume of each unit cell, which will accommodate basically 2 pi by L states of kx. Okay. So, therefore, the total number of quantum states that are accommodated between k and k plus dk will be this volume divided by the volume of each unit cell. Okay. Now, volume of the unit cell is nothing but 2 pi by L the whole cube. So, if you substitute this, you should be getting L cube, just check that, k square dk by 2 pi square. So, this will be a sphere. So, therefore, your surface area for this inner side is 4 pi k square, and therefore, the volume of this shaded region will now be 4 pi k square times dk. Okay. So, divided by the volume of unit cell will now give the, you can count the number of states that is actually accommodated between this differential width k and k plus dk. So, therefore, you have this. Now, what we will do is now define number of states per unit volume of the crystal. So, if you have this chain of atoms in one dimension, we have totally, so the total length will be capital L, right. So, therefore, in a 3-dimensional case, the volume of the crystal will be L cube. So, if you normalize this and calculate the number density of quantum states, okay, accommodated within per volume of a crystal. So, you have k square dk by 2 pi square. So, from this we will define, now you already see that this is some kind of a number density, we are coming to the density of states. So, therefore, the density of states d as a function of the energy. Okay. So, this is defined as basically the number of states or number density of states per unit differential energy. So, that is you have number of states per unit volume of crystal divided by dE. That means, this dk what we have culled out of this map corresponds to a differential energy change dE, right. So, your k is function of E. So, therefore, when you say you have quantized your k, you have also quantized your energy levels. So, therefore, we can define the density of states to be the number of states or number density of states within the crystal per unit differential change in the corresponding energy levels for the change in wave vector dk. Okay. So, this is the definition of density of states. So, if you substitute into this, you get k square by 2 pi square into dk by dE. Or in other words, if you go to your dispersion relation E versus k, take the slope and take the inverse, multiply by this constant. So, that will give you your density of states. You understand? Okay. So, this is your definition. Now, what we will do is, first we will calculate the density of states for electrons. So, all we need to know is the dispersion relation, then we can just substitute into this and we will be able to calculate density of states. So, what is the why do we need to introduce the density of states now? Because now we have so many microstates in a 3-dimensional space that it will be impossible to keep track of each and every state and then calculating the corresponding energy of this state, and then finally how do we calculate a macro scale property out of so many microstates. It is going to be a very tedious and impossible to track task. So, therefore, we are approximating all this with some kind of continuous representation. So, the actual picture of the microstate is a completely discontinuous picture, and now we are making some continuous approximation to that, and in order to convert a discrete to a continuous approximation, this density of states is used. Okay. So, you have actually converted your delta k by delta E to dk by dE, which is now a continuous function, right. So, your dispersion relation is a continuous function. So, this is used now in statistical thermodynamics, because there you are going to sum or do an ensemble average summation over discrete energy states, discrete quantum states, and that if you want to convert into an integral, summation to an integral. So, you have to basically use the density of states to do that, because this number of states here is a discrete number, whereas now the density of states will become a continuous function. So, it is a continuous representation of the discrete quantum states.
So, but the dispersion relation is also having certain quantization, because the case
Right, but then we are not really bothered so much about that, because we are now, for example, for the case of electrons, we have made a parabolic approximation. We know the relationship between E versus k as a continuous function. Similarly, with the phonon dispersion, we know the relationship between omega and k as a sinusoidal function. So, already we have transformed the dispersion as a continuous relationship. So, what we are now doing in the density of states is we are making use of the information from the dispersion curve and representing the counting the number of states to be a more continuous function rather than a number. So, this is particularly used in the next topic, statistical thermodynamics. Okay. So, you may not now understand the relevance why we are doing it, because in quantum mechanics everything is discrete, discontinuous, quantized system. So, going from quantum mechanics to statistical thermodynamics is a big jump. and we are now trying to bridge those gaps. So, the most important concept in that is this density of states. So, now let us try to derive the density of states for electrons. It is fairly simple because we have the dispersion relation there. Do you remember? So, we have E is equal to, if you look at for example metals, okay. So, you can talk about E versus K, you have your conduction band, you have your valence band, and then your Fermi level can actually begin inside this conduction band, correct. So, this is your E F. So, that the conduction electrons are free to move at 0 Kelvin, the conduction band is partly filled, and then at higher temperatures these electrons can contribute to the heat and electrical conduction. So, therefore, for such a case we have already made the parabolic approximation, use Taylor series, and then we have obtained the dispersion relation as what? M star. This is your effective mass of the crystal. Okay. So, although it may look deceptively similar to the energy of a single electron in a quantum well, but this is for the entire crystal, considering the potential energy constraint in a crystal and so on. So, this is your effective mass here. So, now you can calculate from this what is your so dk by so dk by de, and then substitute this into the above expression. And then let me know what is the final expression for density of states. So, your k from this can be written as square root of 2 m star by h bar square times E minus E c. So, what is your dk by de? 2 m star by h bar square the whole or half, then 1 upon under root E minus E c. Okay. Also k also can be substituted from this relationship, so that the density of states should be a function of only the energy E, not k. So, you are converting everything from k to E. So, There is a 1 by 2 missing here, right? Okay. So, anybody completed? Okay, let us say 1 by 2 pi square, this is what I get it, just check, 2 times m star by h bar square, the whole power 3 by 2. So, you have k square, so which will be 2 m star by h bar square multiplied by dk by d. So, you have 1 by 2 plus 1, so that is 3 by 2 coming. Okay. Yeah, so and then you have under root e minus E c. And then we have again a factor of 1 by 2.
Yeah, 2 is a problem.
Now, here this is where for electrons, the density of states, what we are talking about here, we have defined for only plus half spin. So, we have again 2 spins, right, there is a degeneracy. Okay. So, in the concept of degeneracy, what happens, the energy values are same. Okay. So, therefore, this will be just repeated again for the minus half spin as well. So, therefore, you have to multiply the total density of states, you have to multiply that by 2 times. So, then 1 by 2 will factor will be factored out, and therefore, you will have only 1 by 2 pi square into 2 m star h bar square So, this will be your actual density of states for electrons. Is that okay? So, the factor also the spin also has to be accounted for calculating the density of states. So, therefore, it becomes twice of this value. So, I will just mention here accounting for spin. So, if you plot this density of states for electrons, so you have d of E on the vertical axis versus E. So, let us say it starts from, so you understand this picture here, right. So, we are plotting from E0, okay, that is after the valence band, between the band gaps of the valence and the conduction band, for example. So, the conduction band minima will be starting at EC. So, therefore, from this at E equal to EC, what happens to density of states? 0. And from there, what kind of a variation is this? Parabolic variation. So, therefore, if you draw this parabola, so
it's a type of parabolic number because it's a square and a third cube.
yeah, so if about this axis you will get a parabola like this. So, this is you can say if you take d square, so this is a function of E, this is a parabola, right. So, this is the kind of variation. What it means, at the edge of the conduction band EC, density of states is 0, that means there are no quantum states available. The quantum state starts from the conduction band, because that is where the band gap exists, okay. And from the conduction band onwards, the quantum states exist so that the electrons can start filling them, okay. And this will keep growing all the way inside your conduction band. The quantum, as you go to higher and higher energy levels, the number of quantum states increase, so more electrons can keep filling. It starts from the lowest energy level, fills, and then goes to the higher energy level. So, the density of states can grow, okay. So, the density of states actually gives an indicator of how many rooms you have in each floor, okay. So, it does not necessarily mean the electrons have to come and occupy there, but it tells you the potential. So, these are the quantum states that are available for electrons to occupy. So, the actual occupancy itself should be calculated from a distribution function. That is what is done in statistical thermodynamics, okay. So, for example, if you are taking the case of a metal, so where will the Fermi energy come here? So, it is right inside your conduction. So, your Fermi energy level will be somewhere here, and if I want to calculate what are the number of quantum states at 0 Kelvin, that means this indicates the number of quantum states between EC and EF, because the Fermi energy level is defined at reference of 0 Kelvin. Right. So, you can actually substitute into this expression and calculate the actual density of states between. So, one example of how this density of states is useful is you can count the number of quantum states, as simply integral, because what is the definition of density of states? The number of states per unit volume per unit energy interval. So, therefore, if you integrate d of E dE, this will give you the number of quantum states per unit volume of the crystal. So, now I want this from the beginning of conduction band at 0 Kelvin, how many number of quantum states are available to be filled. So, all I have to do is integrate it between EC and EF d of E. So, if you do that, you will get this as 1 by 3 pi square 2 m star by h bar square 3 by 2 EF minus Vc. You can check this, the power 3 by 2. So, this is your electron, this is your quantum state density at 0 Kelvin. Is that clear? So, this is one example to illustrate how density of states is used. So, can you repeat the same thing for phonons now? So, for phonons we will use the Debye approximation. That means we already make a linear relationship between omega and wave vector. So, it is a very much simpler thing than the electron dispersion. So, now you define the density of states here. Now, here instead of energy we use frequency for the case of phonons. Okay, we replace energy with frequency, and you have again 4 pi k square dk by 2 pi by L the whole cube. So, this is your number of quantum states. So, per unit volume will be divided by L cube, and per unit frequency band. So, you have d omega instead of dE, and remember there are 3 modes. You have 2 transverse modes and 1 longitudinal mode. So, therefore, you have to multiply this by 3. Okay, in the case of electron you have spin, therefore, you have to multiply the density of states with 2 times. Now, you have 3 modes, so density of states you have to multiply by 3. So, can you substitute quickly your d omega dk by d omega, which is 1 by Vd, and then tell me what will be the final expression. I will give you the expression, just check this. Okay. So, therefore, if you plot this d of omega versus omega, this should vary as omega square. So, at omega equal to 0, this is 0, and then it should go up. So, this is your Debye model, it should go up like this. And what is for the optical phonons? Dk by d omega? Infinity. So, therefore, the density of states for optical phonons will look like this. So, this is for the Debye model, this is the Einstein model. Is it clear? Right. So, now we can extend this to other nanostructures. For example, if you look at a nanofilm, okay, something like this. So, you have coordinate in the z direction where you have a nanometer dimension, maybe 10 nanometers, whereas in the x and y coordinates it is not confined. So, the confinement is only in the z direction. So, in this case the energy which is a function of kx, ky, kz now will become discrete only in the z direction because of the confinement, right. So, it becomes quantized in the z direction, whereas in the x and y direction it will have the crystal wave vector. Okay. So, that is you have h bar square k xy square by 2 m star. So, that means this is for the energy versus k relationship for the crystal, you have m star, and for the z direction you have specifically quantization happening. Therefore, you have n square h bar square pi square by 2 m star d square. So, this is again nothing but h bar square k z square by 2 m star, where k z you have replaced as n pi by d, because this is your confinement with d. Okay. So, therefore, what is happening in this case, the dispersion k x y is continuous, the dispersion between E and k x y is continuous, understand, but this k z is now discrete. So, if you calculate the density of states for this and plot it, for the case of electrons in a crystal without any confinement, that is a 3D crystal, you get like this, right. Now, for the case of electrons which are confined in one direction, this now will become a staircase profile because of the quantization in the z direction. So, corresponding to n equal to 1, this is n equal to 2, n equal to 3 and so on. So, similarly, if you put confinement in two directions, this will end up being just lines, and if you put confinement in all the three directions, it will be just points. So, these are called quantum dots. So, these are you can say these are just stair step profile. In the case of 2D constraint, you will have quantum wires. So, that means like this, just discrete vertical lines, and in the case of 3D confinement they become just points, quantum dots. So, these are the ways how the density of states can get modified depending on also the quantum confinement effects. Okay. So, we will stop here because the next professor is waiting. So, we will start with statistical thermodynamics in the next week. Okay. Thank you.